Faraday's law and induced electric fields 2. The figure shows a region of radius r containing a B field that is increasing with time. Note that there is not a material loop at the region's edges. The magnetic field simply stops at the points in space indicated by the boundary shown. If there were a metal loop around the region, in which direction would there be an induced current around the loop? Well, we would need to use Lenz's law here, and we'd say the magnetic field is increasing towards us, and so nature doesn't like change, so we need to fight that increase towards us with our thumb, pointing our thumb into the page, and that would be clockwise. If there isn't a metal loop, would there still be an induced electric field at the region's boundaries? Yes, there would. Into the figure, draw and label electric field vectors to show how the induced electric field is directed at various points around the boundary. As we said earlier, the electric field would be in the clockwise sense, so we just want to draw a couple of electric field vectors here, tangent to the boundary. That would be the direction of the induced electric field. Assuming we know that the magnitude of the magnetic field conforms to the equation B of time is equal to gamma times T, where gamma is a positive constant, derive equations for the electric field at locations where R is less than big R, and then also at locations where R is greater than big R. Finally, graph the results. Hint: when using Faraday's law to do this, we can ignore the negative in the equation. We essentially took that into account by the direction of our E field vectors in the figure. For R less than big R, we're going to have Faraday's law. I'm leaving the negative off because we took that into account when we were deciding what direction things went. Here we are looking for the electric field, so we definitely need this portion, the right portion of this equation, and we have some information about the magnetic field, so I think we should keep this part in as well. Well, isn't it true that we can sort of rewrite that as d dt? Remember that magnetic flux is essentially B times A. The area is constant here. That area is for an R that is only that big, less than big R. That's going to be pi little r squared. And the rate of change of the magnetic field is then just going to be the derivative of this equation that I've now boxed in right here near the top. If you differentiate that with respect to time, that is simply gamma. The left side of this equation looks like gamma pi r squared, and on the right, at every point that is equidistant from the center here, an r distance away, this electric field has the same magnitude, which means that that is a constant and can be moved outside the integral. And now we're just going around the circle. What we have on the right side is E times 2 pi little r. And when we solve this for E, what do we get? I see a pi that's canceling. That r cancels one of those, and I think we get 1/2 gamma r. That's the magnitude of the magnetic field, electric field, excuse me, when we are inside big R. What if we are outside big R? Then what do we have? Well, now little r is bigger than the region where the magnetic field is changing. What's going to be different? D dt B is going to be the same, so that gamma is going to be exactly the same as it was. The area now that we are considering is only going to be up to big R, because the flux isn't changing all the way out to little r. It's only changing up here to big R. It only goes that far. But the electric field that we're talking about is the one that is little r away, like that, which means that for this case, the electric field is going to be what? Pi cancels, but I think that's just about it. The 2 has to go in the denominator, and the little r has to go in the denominator, so I think we're going to get gamma big R squared over 2 little r. If we graph that, what kind of graph are we going to produce? When r is less than big R, you can see it's linear with respect to little r. We would have a curve that looks like that to the first power. The electric field is proportional to r up to that point. And then beyond that, it slopes off proportional to, you can see the little r in the denominator. The electric field is proportional to 1 over r, like that.